Hi, I am John Martin, a professor of astronomy and physics at the University of Illinois Springfield. My co-author Bill Ray and I are contributing two talks about the application of low-resolution filter wheel grating spectroscopy to observations of Mira variables. Now, my talk is going to be about the theory, and Bill is going to be about application. He will be talking about three Mira variables that he has analyzed using this process. To start with, let me tell you a little about filter wheel gratings. And if you don't know about filter wheel gratings, you really should. Filter wheel gratings are an easy way for non-professionals to start doing spectroscopy. They are a grating that can be put in a standard slot in your filter wheel. And by just imaging through it like a regular filter, you can record spectra. The spectral resolution can vary, but it is normally sufficient to measure significant spectral features and do spectral classification. I have a website listed here at the bottom for more general information about how to get started with these gratings. Now, the spectra for this study that I'm talking about today were gathered by Bill Ray, who is observing at about 43 degrees south latitude in Christchurch, New Zealand. He's using an 8 centimeter apochromatic refractor, that's about a 3-inch diameter refractor, using an ATIC 414E mono CCD. And with that, he's using a Paxton-Hawksley Star Analyzer 100 grating. This is a very typical off-the-shelf setup that should reproduce what a lot of non-professionals are out there using. Now, at the SAS Symposium in 2016, we reported on a project exploring the use of filter wheel grating spectroscopy to observe long-period variables. Longer period variables have always been a favorite target of non-professional astronomers because of their large amplitude changes in brightness. We focused on Mira variables, and the goal of the work has been to develop a relatively simple to implement application for filter wheel gratings that adds value to what non-professionals are doing with these targets. Now, our initial work demonstrated that spectra observed through filter wheel gratings detect differences between the spectral classes of Mira variables, and the spectra were also sensitive to changes in the spectrum around the periods of the variables. That is, as the Miras went through their periods and got brighter and fainter, we could see the changes in the spectrum with the star analyzer gratings. Now, one issue, though, with broadband photometry of late-type stars. And by broadband photometry, I mean like Johnson UBV or Stromgren or Salone filters. The issue with broadband photometry of late-type stars is that the color indices are not very good for measuring the change in spectral type or surface temperature. Because the spectrum of M-type stars is dominated by broad and deep molecular absorption bands with very little exposed continuum that can show the underlying black body. Now, Wing developed a narrowband photometry system to measure the variability in late-type stars using the depth of the titanium oxide molecular absorption features. The changes in the TIO features correlate well with the changes in spectral type and effective temperature of the star. Now, low-resolution spectroscopy is basically just narrowband photometry, because when you think about it, a single spectral resolution element is basically a very narrowband filter. And the flux can be added together across the spectrum to synthesize photometry. It is probably more accurate to state that multi-band photometry is just ultra-low-resolution spectroscopy. I know you guys are sick of hearing me say that, but it's true. Multi-band photometry is just ultra-low resolution spectroscopy. So we can apply similar principles here. Using the principles of wing photometry, Bill Ray developed an approach to measure the spectral changes in Mira variables. That work is outlined in his 2019 Journal of the AAVSO paper. It's listed here. Now, the basic idea he came up with is to take the ratio of the relative flux in a spectrum at the maximum depth of the titanium oxide feature, which is near 719 nanometers, and compare that to the pseudo-continuum flux at a point near 754 nanometers. Now, the application of principles of wing photometry to analyzing spectra works really well for early M-type Mira variables. As you can see in this graph, there is a nice linear rise in the wing AB ratio from spectral type M2 through M7. but it doesn't work as well for later types. Now, the reason why the ratio does not work for later cooler spectral types is that later than spectral type M6, a vanadium oxide band begins to grow in the blue side of the pseudo-continuum flux point near 754 nanometers. This is visible clearly in the template spectra here on the left. Wing realized that the bandpass of his B filter included this region, so he recommended that his A to B ratio only be used for spectral types hotter than M6. You can see that when we get down here, you start to see those vanadium oxide lines creep in just to the blue side of that point you want to measure the flux. Okay. Now, in filter wheel grating spectroscopy, which is lower resolution and shown on the right here, the spectral features are blurred together, and that's as a result of the low spectral resolution just blurring it out. So as a result, like with the narrowband wing filters, the wing AB index cannot be used effectively with spectral types that are cooler than M6. And some Miras, like R oct that is shown here, are cooler than M6 over much of their cycle. Now, other astronomers, notably Azizi and Mitarabi in 2015, suggested other points in the spectrum could be used to replace the wing B pseudo-continuum flux. But Bill Ray's work showed that those suggested workarounds were only practical when you apply it to much higher resolution spectroscopy, and they are not effective at the low resolutions you get from filter wheel grating spectroscopy. Now, for those of you who are unfamiliar with low resolution spectra of later type stars, the deep notches that you see here in this spectrum are molecular absorption bands. At high resolution, those are going to resolve into lots of narrow individual absorption lines like you've seen in textbooks. But at the low resolution just blurs them together. Now, a spectrum of an A-type star at this resolution, you'd be able to see individual absorption lines of atomic hydrogen that are nicely spaced out. But notice that the H-alpha emission that is associated with Mira-type variables, that is not visible at this low resolution. In M-types, like Mira variables, the absorption lines are so densely packed together that they blur together into these large masses. The quote-unquote peaks that we see between are where you have less absorption. And they are not necessarily points that measure the continuum, because as we saw with the wing B band, nearby absorption can erode and depress the peaks. That is why we call these pseudo-continuum points. So having found we could not apply the principles of wing photometry to the coolest spectral types, we went back to the basics. We remembered in our 2016 pilot project that changes in spectral type are visible in the filter wheel grating spectra. You can see this in the animation shown, how the spectrum of Larsen shifts towards the red as the target gets fainter and cooler. The relative heights of the quote-unquote peaks between the absorption bands change in a way that we hope can be related to spectral type. Now, a person who's trained in the MK, the Morgan and Canaan process, could classify these spectra accurately on site. However, efficient precision practice of spectral identification requires many hundreds of hours of experience. Some would say even thousands or a whole career. Now, my goal is to, like the wing did with narrowband photometry, identify a quantitative measure that is relatively easy for anyone to calibrate without hundreds of hours of practice. And we want to be able to apply it without that extensive training that's required to use the MK spectral classification process. Now, the graph that is shown here on this slide shows the spectrum of Mira variable R oct that notes the pseudo-continuum points identified by Kirkpatrick et al. Now, the wing A TIO absorption point is also marked. Notice that the wing B point for measuring the continuum in the wing filter system correlates with the Kirkpatrick C3 pseudo-continuum point. The alternate continuum point that was proposed by Azizi and Mitarabi correlates with the C2 Kirkpatrick point. Now, if we were to take and measure these continuum points ratios for a pure black body, For that pure black body that has no absorption features, the Kirkpatrick pseudocontinuum points would show a smooth and probably detectable variation with temperature. But as we've seen, M-type spectra are not pure black bodies. The underlying black body has been significantly modified by molecular absorption features in the photosphere. So to figure out what we might see for real M-type stars, we use the Pickle spectral library to predict how the Kirkpatrick pseudocontinuum points change with spectral types. The M-giant spectra in that library, and by a giant I mean luminosity class 3, those spectra most closely match the spectra of M-class Mira variables. Now, the flux calibrated spectra in the templates have a higher resolution than the filter wheel grating spectra. We did not artificially reduce the resolution of the template spectra, but we did measure them in the same manner that we measured our grading spectra. Now, the two pseudo-continuum point ratios that showed the most promise with the Pickle template spectra were the C1 to C3 and C2 to C5 ratios. We predicted that the C2 to C5 ratio, that's shown here in red, that it should work as cool as spectral class M7 or M8. Notice that after M8, it becomes pretty flat. Okay? That's better, though, than the wing AB ratio, which is only going to work for stars that are hotter than M6. Now, note also that the C1 to C3 ratio shown in blue continues to vary in spectral types as cool as M10. Now, there is some aliasing because notice that M9 and M4 have about the same ratio value, right? But if we use it in conjunction with C2 to C5, that should be pretty constant out at M9 and M10, we ought to be able to work out from the C1 to C3 and C2 to C5 ratios what the spectral type of the star is, maybe even all the way out to M10. Okay, so at this point, we have a hypothesis for how we could measure cooler Mira type variables near minimum, but we need to test it out. Along the way, though, of testing it, we uncovered 5 important considerations that I have listed here. Our aim, of course, was to formulate a process that is as simple to use as putting a grating in your filter wheel. So we need solutions that anyone can easily implement. Now, let's take a close look at these one at a time. Now, generally speaking, we know that it is easy to do a relative wavelength calibration, but it's much more challenging to do a really good absolute wavelength calibration. And this is especially true for filter wheel grating spectra, which rely on measuring the position of the zero order image to set the 0 point for your spectrum and its wavelength scale. In our experience, it is not difficult to set the 0 point of your spectrum within about plus or minus 5 nanometers. That turned out to be about 3 pixels in Bill Ray's setup. Now, to be conservative, we expanded that margin of uncertainty out to plus or minus 7.5 nanometers. And here in these graphs, the margin of 7.5 nanometers on either side is shown with the dotted lines. Okay. Now, it turns out then that we're interested in the peaks, right? That the pseudo-continuum points should be peaks in the spectrum. So when we go in and measure this automatically, we can take the peak flux value that lies within 7.5 nanometers of the expected wavelength. Do a similar thing to measure the depth of an absorption feature, where we took the minimum flux point within plus or minus 7.5 nanometers of the expected wavelength. Now, notice that one of the benefits of this approach is that it allows a knowledgeable person to measure pseudo-continuum points by eye, even without wavelength calibration. If you know what the spectrum is supposed to look like, you can identify that C2 or C5 point without a wavelength calibration. And actually, for making this process accessible and easy to use, there is an advantage to being able to measure the pseudo-continuum points by eye without any formal wavelength calibration. We were able to detach it from having a really accurate wavelength calibration to do it. Now, the second issue was that the drop-off in efficiency of silicon detectors happens in the near-infrared part of the spectrum. That is that, as we see in this plot of the efficiency of a silicon-based CCD, that it drops off towards the near-infrared. by quite a bit. And M-type stars, like the one shown down here, put out most of their flux in the infrared. So the spectrum is mostly recorded in that declining efficiency part of the spectral response curve for the CCD. Now, a typical CCD is going to have a 20% lower sensitivity at C5 than it does at C2. Longer exposures and image stacking can help to mitigate this. But that C6 point, the reddest, longest wavelength one, is probably unusable in spectra recorded by most CCDs. That's something we had to think about. And so we didn't use the C6 point at all. Now, the third issue is related to the second, in that as one goes to cooler spectral types, the spectral flux shifts redward, and in Mira variables, as it gets cooler, it's also getting fainter. Now, the graph shown here on the right shows the spectrum of our oct at maximum on the bottom and at minimum on the top. Okay, this is actually, for minimum light, the best spectrum that Bill Ray could get at minimum light with his setup. Now, notice how much more noise there is in the blue end of the spectrum at minimum light. Now, that's going to affect the C1, C2, and TIO measurements. Now, conceivably, this could be improved through longer exposures and stacking more images. But practically speaking, we struggled to do that with Bill's setup. And unfortunately, though, this has a clear effect on the C1 point. And when the star is coolest and faintest, we want that C1 point because we predicted that the C1 to C3 ratio would be sensitive to differences in the latest coolest spectral types. This probably means it rules out using the C1 to C3 ratio in some instances. Okay. The final two considerations we have relate to calibrating the process across different telescopes and camera systems. Now, the spectral resolution is going to depend on the grating used and the distance between the grating and the imaging plane. Now, the graph on the right here are spectra of the same star taken hours apart on the same night with two different telescopes using the same type of grating. However, because of the placement of the grating, there are different resolutions. The higher resolution spectrum, shown in orange, shows much sharper features. The lower resolution spectrum, shown in blue, shows that those features kind of blurred out, as is going to happen at lower resolution. Now, also remember, in addition to this, the spectral resolution, the spectral response of the CCD and telescope combination is also going to affect the relative flux across the spectrum. Okay, to address all these issues, we introduced spectroscopic comparison stars. And the comparison stars are selected for their low spectral variability to cover the range of spectral types that the target is going to progress through over its cycle. This is very similar to the way you would select photometric comparison stars. Now, as an example, the table at the bottom of the page shows the target R-oct and the 4 comparison stars that Bill Ray observed with it. Now, ideally, that list of comparison stars for R-oct would include a star with a spectral type of M9 or later. But one of the challenges we have for selecting comparisons is finding very late type M giants that are not themselves very long period variables. So we couldn't in this case. Now, let's get to some of the data from R-oct here. When we tried this with R-oct, this graph shows the C2 to C5 ratio for the comparison stars as a function of their published spectral type and effective temperature. R-oct is shown separately over here on the right. Now, as we predicted from the Pickles template spectrum, there is a clear relationship between the C2-C5 ratio and spectral type. Okay? We can conclude from this data that R-oct, its range shown over here, ranges in spectral type between M6.5 and M9. Now, it clearly never got as hot as CQ-oct, which has a spectral type of M5.5, and it clearly got cooler than BW-oct, which has a spectral type of M8. This is consistent with the published range of R-oct that is between M5.3 and M8.4. Now, looking more closely at this data plotted over time, the plots of the ratios of R-oct as a function of time show that what we expected for the wing AB ratio shown on top, which does not register a clear variation through most of the cycle. Now, in the middle panel, we show the brightness of the star measured in the visual and the V band. Okay, we can see where the maximums and the minimums occur. And we see that there is some response in the wing ratio at the maximum brightness. But when the star is cooler, the wing ratio basically just descends into noise. Okay, the Azizi and Mitarabi ratio, which is designed to avoid the wing ratio shortcomings, that's shown here on the bottom, was also not as effective at low spectral resolution. In fact, we saw kind of almost no response from it at the brightest point in the star cycle. Now, let's look at C2, C5, and C1, C3. As predicted, the C2 to C5 ratio varies clearly in sync with the brightness. See on the bottom here, the C2 C5 ratio goes up with the brightness and down with the brightness. This supports our hypothesis that it is an effective measurement of spectral type in these cooler stars. We also predicted, as seen here, that C2 to C5 ratio would flatten out near minimum brightness when the target is coolest. Our work with the Pickles template also predicted that the C1 to C3 ratio shown on the top would be more effective to measure the change in spectral type when R-oct is coolest near minimum. But that decrease in flux at the C1 point led to an increase in the signal to noise at C1, and it makes it impossible for us to tell in the data we have if there is a response of C1 to C3 when the star is coolest, or if we're just seeing the noise in the C1 point. This is something we still have to work on to figure it out. So in summary, our work demonstrates that variation in spectral type can be measured quantitatively using low-resolution spectroscopy. And we've extended the sensitivity with spectral type to later and cooler types than can be done with the wing AB ratio. And we're hopeful that with this new information, observers doing photometry with Mira variables are more likely to consider adding a grating to their filter wheel and a new dimension to the data they are gathering for these long period variables. Thank you for your attention. And here's a short bibliography for reading more about this work. And please, I also encourage you to watch Bill Ray's talk, where he's going to present the application of this process to 3 Mira type variables.